is my screen visible? Say yes or no. I'm just confirming with you all. One can respond. Okay, fine. Thanks. I couldn't see the response. Okay, no problem. I think it is visible now. Okay, let me go for slideshow. Yes, now I'm able to see the replies. I also disabled the annotation so that we may not get further disturbance from the unknowingly from other participants. Okay, already they have introduced about me. So thanks for your good introduction, madam. Now let us get into our topic. Let us have a discussion. 1 minute. Let me get ready for this. I'll make few settings before I begin. Okay, fine. Thank you all. So I have confirmed with all the participants. My voice is audible. It's clear, and also my screen is visible. So both are important. And I have muted you all. Kindly bear with me. And let us start discussing about the basic concept first before I move on to the fax controller. So we are all aware that power system is non-linear, and as a customer, what do we expect? We expect a quality power. And when do we say quality power? We are all aware that in terms of voltage, in terms of frequency, and the reliability, cost. So these are the factors which determines the quality power, and it should be harmonic free. And we are all aware that we as power system operation operator should ensure the real power balance and reactive power balance. When I say balance, the generation must match the absorption or the power demand. So which include losses also. So we are aware about the power balance equation. Power generation that must be matching with the sum of the power losses in the transmission line and the power demand. Okay, so we need to ensure that the load is being met. Both real power demand and reactive power demand, it is being met okay continuously. For that we should have a adequate source of power, real power generation and reactive power generation. So that is one requirement. And we also another requirement is that optimum cost. So when I say optimal, it should be fuel cost or what are the that should be for that economic dispatch. We have simulating it and try to find out. So for the available load, how to what will be the minimum fuel cost which we are working, that will be decided. So that minimum at minimum cost we should be able to or optimum cost. Nowadays we speak about optimum with the help of evolutionary algorithms. Okay, so the optimal is the best solution, and with also with minimum ecological effect. And there are some parameters like frequency, voltage. These parameters, especially frequency, voltage, very important. So we should maintain a constant frequency and constant voltage. But in ideal case, it is possible nominal voltage, but we have some allowable limits. Okay, that permissible limit. With if that voltage is falling within that acceptable voltages, then we call that voltage is stable, and that is acceptable. For example, 1 per unit is the nominal voltage. If I say 10 percentage, for example, I'm saying 10 percentage plus or minus 10 percentage is allowed. That means what? I can have the limit range from 0.9 per unit to 1.1 per unit. In case of frequency, 50 hertz is the normal frequency. And in voltage, I was just giving example. It is 10% plus or minus 10%. Sometimes we take plus or minus 5%. If it is 5%, is 0.95 to 1.05. If it is 10%, it is 0.9 to 1.1 per unit. So any voltage falling below this lower limit, we call it as under low voltage, and any voltage which exceeds beyond the that upper limit, we call it as over voltage. And frequency, in case of frequency, 50 hertz is the normal frequency. If I say plus or minus 1%, what is 1% of 50 hertz? it is 0.5. So if I subtract and add, what will I'll get? 49.5 hertz to 50.5 hertz. If I say plus or minus 3%, 48.5 to 51.5. So just example I'm giving. So what I want to convey here is we need to see that constant frequency or acceptable voltage and frequency are existing in the power system. So these are the requirements for the power system to be in stable condition. Now, in terms of voltage regulation, we know that what is the necessity for voltage regulation, because all equipments, we are aware that it is designed with certain voltage level, that rating will be specified while we are purchasing that equipment, and its performance will be affected if the voltage level is not maintained properly, and it will have further impact. So for that reason, one need to take care of voltage regulation. Okay, and we are all aware about the cross coupling loops. May know what are the two loops cross coupling we might have studied. There are four parameters. One is real power, P, and reactive power demand, and Q, and then del, and then voltage. So we have to a cross coupling loop that you might be aware. That means these are all parameters, power system parameters. When I say voltage, voltage angle, or del, whatever may be, real power, reactive power, are interrelated. When I say interrelated, when one parameter is changed, it will have effect or impact on the other parameters. What is the meaning is, other parameter also will be get disturbed, or it will have a control over the other parameter, that also will be changed or modified. For example, we know that P del, so P del, so that loop, so that means whenever there is a change in the del, there will be a change in the real power, and whenever there is a change in the reactive power, there will be change in the whenever there is a based upon the availability of reactive power, voltage will be changed. There are two loading conditions. What are the two cases possible? One is light load condition, another one is peak load condition. In case of light load condition, that is when loading condition is light, so it is not heavy. So during light load condition, we are all aware that the voltage, we face the problem of over voltage. What is the reason? Because as many of the loads are not operating at this light load condition, reactive power consumed will be less, and the reactive power will be more. So surplus, due to the surplus of reactive power, voltage will be more. So what do we infer from this is, voltage and reactive power are having close relationship, are strongly related. That means whenever based on the prevailing condition of the reactive power, voltage will vary. So in simple words, I can say that voltage instability, one of the main factor is the deficit of reactive power. I have done my research in the power system voltage stability analysis. I have developed some artificial neural network model for online assessment of voltage stability margin by using a suitable voltage stability index. Okay, that I will discuss later. And I also worked on few fax controllers to enhance the voltage stability. That's why I'm very much interested in discussing about the voltage stability. And so with this, I will try to conclude here. That is for this regarding this topic. So whenever we are having surplus of reactive power, we face the problem of over voltage. Whenever we are having deficit or shortage of reactive power, we face the problem of low voltage. So but do we expect the normal voltage, that means voltage level falling between the within the acceptable limit. So for that, what we need to do, we need to maintain the proper reactive power balance. So for that, we prefer fax controllers. So the objective of the fax controller to ensure that there is a proper reactive power balance. When I say reactive power balance, it is nothing but compensation. We are using compensation technique, series and shunt, especially to match the generation with the demand. Okay, I hope you are able to understand the importance of reactive power and the voltage. Let me move on to the next slide. 1 minute, it got struck. Okay, what is reactive power? Many of you are aware there are so many definitions and concepts. We might have, as a faculty, we are interested to explain a lot to a student. So there is no much time to explain all those things, because you are all aware, you are all faculty, and you might have taught your students. Just to, let me tell the significance of reactive power. Okay, and how reactive power is measured, what is reactive power, what is the importance, all those we might have taught to our students. Now let us try to see the function. So eight main function is to that. I might have given the next slide. Okay, it is required to maintain a proper voltage level that I have discussed already. That in turn will deliver active power. Okay, I told uh, deliver active power should be transferred through it. It will be transferred flowing through the transmission line. For delivering the active power, we need the proper potential or voltage. Okay, so for maintaining that voltage, we need this reactive power. And other like induction motors and other loads require reactive power in order to convert the flow of electrons into useful work. And we know that when there is not enough reactive power, voltage sag that will be a problem. Voltage sag will be occurring, and it is not possible to push the power demanded by loads through the lines. I told that for delivering the active power, for the required power to transfer to be through the over the transmission line, we need a proper reactive power as it is maintaining the proper voltage. Okay, so this is the significance of reactive power. And in this slide I have given that it is essential to move active power through transmission and transfer same only. Now, let me take few seconds to recollect the concept regarding reactive power sources and reactive power observing devices. How do we generate? What are the examples or what are the devices in power system components which are having the capability of generating reactive power and observing reactive power? So as you see here in the diagram, see here, there are synchronous condenser, synchronous generator. Then we have got a capacitor and line charging and tie lines. So left hand side. So what you observe is in the first three cases we have wall. That means it is controllable. So whereas in the remaining two we don't have that wall. That means it is fixed. So that is the difference. And right hand side, if you see, it is tie lines, reactors, loads, generators, regulator, and losses. So what is the example here is this will sources, and these are all observing devices. For example, in case of synchronous condenser, based on its excitation, you are all aware that synchronous condenser can be made to act as a generator of reactive power and absorption of reactive power. The condition of over excitation, we can make it as act as a generation of reactive power. It will generate reactive power and it will observe reactive power when it acting under excitation, when the excitation level is low. Okay, this we have three cases: normal excitation, under excitation, or excitation. So by varying the excitation current, we can make the synchronous condenser to operate in both the modes, in generation mode as well as absorption mode. And for example, this capacitors in transmission line, we have got a series capacitor. So capacitor generally we are aware that it is has the capability to generate reactive power. It will generate only reactive power, and inductor will observe the reactive power. Okay, these 2 points to be remembered, and you're all familiar with it. And in case of transformer, yes, in case of transformer, as it got inductive, so it will observe reactive power. Okay, and underground cables, so major dominant effect is capacitive. Therefore based on the net effective capacity effect or inductive effect, we can say any power system component we can classify into either a generation or observing device. Okay, so with this I will try to end this slide. So I hope you are all able to remember the concept of generation, absorption, reactive power. And though we are enjoying the benefit with reactive power, we should know that always we are interested to locate or connect the capacitor bank or the static work compensator at the low end, because voltage stability is load driven, whereas I would try to make you all to remember that power system stability is classified into three categories. One is what is that? rotor angle stability, second one is frequency stability, and third one is voltage stability. Let me repeat once again. Power system stability can be classified into three categories. First one is rotor angle stability, that is further subdivided into small signal stability and transient stability. Okay, transient stability is a type of rotor angle stability. That's why we are equilibrium criterion swing curve we are studying in detail. And in case of voltage stability, based on the nature of the disturbance occurring, we can classify into two categories. One is small disturbance voltage stability, and another one is large disturbance voltage stability. What is the small disturbance and large disturbance? As the name indicate, based on the nature of the disturbance occurring in the power system. For example, if the load is varying in a gradual manner, so slowly in a steady manner, in that case the disturbance nature, that is it is slow, therefore we call it is small perturbation, so we call it as small disturbance voltage stability. Suppose the disturbance in terms of outage, when I say outage, out of service of maybe generator outage or line outage, so transmission line may be out of service or generator may be out of service. In that case, what will happen? We call it as major outage, so major disturbance or large disturbance. That's why we call it as large disturbance voltage stability. Okay, so now what I want to say is here this is the classification that you should remember always as a power system engineer. And now this reactive power will be source will be located generally at the load side. Why I was telling that? Because we should know the difference between rotor angle stability and voltage stability. Voltage stability is driving factor is load, that's why it is called load stability. And generator rotor angle, it is the driving factor is rotor angle, therefore it is called rotor angle stability. Okay, it is generation side, this is load side, that is the difference. And this if they we are trying to transmit reactive power over a long distance, what will happen? We face the problem higher losses due to this I square x losses. So you can, for that I'll give an illustration. If a tank is there, just follow this, don't confuse yourself, just please pay attention and try to understand this example. You might have taught this example to your students also, I hope so. So if I want to fill a tank with water, so nowadays we have got motor, we'll turn on switch on, it will be automatically filled. Just this example, this is unlucky to make you understand the importance of rectifier, and we need to place it in the near the loads side. Okay, so we have got a ladder to climb up and fill the tank. And we'll be having a bucket. A person is carrying a bucket and filling it with water, and walking over the climbing over through ladder and trying to pour that water into the tank. So now what I want to say is reactive power is waterless power, but it is also doing some work. But it is being delivered back to and fro, it is oscillating to and fro, and that will be coming back. So that's why we are not pricing it for it. And reactive power, what I will try to compare here is that ladder is the transmission line. Ladder I'm considering as a transmission line. Okay, if the more weight is there, ladder will collapse or will break. So in that case, if more power flow more than its rating, that is a limit for everything, so we cannot keep on adding weights. So in the ladder, or if the what more weight is there, what will happen? Based on the weight, that ladder will get it will be broken. So in that case, we one need to take care. Similarly, the transmission line is compared to the ladder, and now the person is climbing up with the bucket filled with water and trying to pour it in the tank. Now that water is what is compared to that active power. Okay, now the person with the bucket, after pouring it, now useful work is, our objective is to get the tank filled with the water. So that is the real power delivered. After delivering the real power, so for carrying what for carrying that necessary amount of water, the person's strength, the bucket size also matters. If he's having small size bucket, small amount of water. If he's having big size bucket, he'll have more amount of voltage, more amount of real power can be transferred to that. That more amount of water can be carried and poured into the tank. So I hope you will be able to understand this illustration. So I'm comparing that water as the real power and bucket as the reactive power. So and then later as a transmission line. Just for example, don't confuse you a lot. And after pouring that water, he's returning back with the bucket, empty bucket, to the same place. Therefore, we know that the work will not be done. But strictly speaking, after that work is done, the reactive power is returning back. Okay, so this will make you to understand. And suppose if a hole is there in the bucket, just make you understand saying, just it's, imagination only. If I am asking you to imagine that, assume that there is a hole in the bucket, small hole. If I am going to transmit, or if I'm going to carry that bucket with water over a long distance, what will happen? Due to leakage of water will be there, and the destination, less amount of water will be poured. Similarly, also this reactive power, due to this I square x losses, if the distance is large, so more amount of reactants, and because of this high I square x losses, what will happen? Less reactive power will be transmitted, and reaching that final solution, what destination. So this is that's why we always prefer to locate the reactive power source, especially this capacitor bank and shunt capacitors or SVC at the load side. So okay, now let us move on. This to this I have seen, I have discussed about few basic concept. Now let us see the definition for FACS. So it is an acronym for flexible AC transmission system. So we know the difference between the flexible FACS and FACS controller. When I say FACS, it is a system. What system? Alternating current transmission system. Whom do we call as a flexible? Are you a flexible person? So when we say flexible, reliable, flexible. So having the capability to adapt to based on the situation. So here also, this power system can be altered or such a way that our objectives are being fulfilled. So the main objective of flexible AC transmission system is to enhance the power transfer capability of the transmission line. Let me repeat once again, the main objective or ultimate objective of the fax controller or any fax device or fax is that to increase the and enhance the power transfer capability of the transmission line. Okay, so when I say power transfer capability, it can not only increase, it will have a control. This is the definition as per the book, but in my point, in addition to enhance, it will control. When I say control, either it can be increased or decreased. Okay, so based upon the prevailing existing loading condition. So based on requirement, if I want more amount of power, in that case I need to enhance. If I want less amount of power, I need to decrease. So it is just we are trying to operate near the limit. So we are trying to at full extent, we are trying to utilize it. Okay, so that is the concept of fax. And fax controllers, as you are aware, and we are using the power electronic based power electronic controllers for this. Nowadays GTO we are using, and so many advanced power electronics are being used for manufacturing this fax controller. And power electronics, due to its futures, it is finding application in the designing of fax controller. So it is fully and fully based on the power electronic concept. It is a power electronic based system. And in addition to the power, apart from that, some static equipment may be used. This the same objective is same only, to provide control over the transmission system parameters. Yes, what are these transmission system parameters? Any idea? This is a symbol for a fax controller, you might have seen, because when I say power electronics, so the main component is thyristor. So thyristor valve is shown here. So therefore this we are using this symbol as this as a symbol for fax controller. Now any idea about the transmission system parameters? Now time is 10:40. I told I'll be ending by 11:30, so I'll go fast. I have to show you the demo of the how STATCOM is used for enhancing the voltage stability with a PV curve, that I'll be demonstrating after 11 o'clock. Okay. If you're not responding, no issue. I'll continue due to time condition. Yes, inductance, capacitance. Okay. Thank you, sir, for the reply. Okay, when I was asking about this parameters, so for that I have received reply as inductance and capacitance. Okay, that is okay. parameters we will always remember resistance, inductance, capacitance, transmission line parameters. But here I'm going to yes, as you said, this RLC. So that is correct. Now we might have studied, we have derived the formula for real power and reactive power in a lossless transmission system. We might have taught to our students also. From that, we will try to conclude this power flow. The main objective, there are so many applications of facts, but the ultimate or the important application or the first foremost objective of any fax controller is to enhance the power transfer capability of the transmission line. So it should have a control over the real power flow which is flowing through the transmission line. So now I should be able to know how I can achieve this. What is my objective? What I should achieve, that I'm clear. How should I how will I achieve, or how should I achieve? That is my second question. For that, I should be able to know the relationship between the power system parameters. I told that all the power system parameters are interrelated. PDEL like QV. So now this real power and reactive power flow, which are flowing through the transmission line. So how it is related to the other parameters in terms of voltage or reactance or del. So that is what we are going to see now. Okay, I hope many of you are aware about this equation. I'm not going to derive this equation. Using phasor diagram, we can derive this equation, or from this above two bus system, we can derive it very easily. So that is a simple derivation. So after deriving, we will be getting this equation. This is the active power flow and reactive power flow equation for this simple two bus system. And V1 angle del 1 sending end bus voltage, and V2 angle del 2, let it be voltage of the receiving side, or yes, load side. And we are ignoring the resistance. Generally reactance will be more when compared to resistance. We are ignoring it. And we are having complex power flowing, that is flowing through the transmission line. It is sum of P and Q. So power is flowing from bus 1 to bus 2. That's why it is denoted as P12 and Q12. And this is the important equation which we are supposed to remember. Okay, one is real power flow and reactive power flow. Real power is given in terms of V1, V2, X. That is V1, product of V1, V2 divided by X into sine del, where del is nothing but the difference of del 1 and del 2. And Q12 is equal to V1 square divided by X minus V12, sorry, V1, V2 divided by X into cos del. Okay, so from this, what we understand is there are three important parameters which based on which this real and reactive power can be controlled. What are those parameters? One is voltage magnitude. So voltage magnitude, I can be both the transmission and connecting both the end that two buses. So V1 sending end voltage and receiving end voltage, and transmission line impedance or transmission line reactance. When I ignore this resistance, it is only reactance and total line reactance. And third parameter is phase difference. What is phase difference? Phase angle difference. So voltage angle. So difference in the voltage angles, del 1 minus del 2. So these are the three important parameters, or we call it as control attributes. Attributes means parameters or variables. We can call it as control parameters. We can call it as control variable. We can call it as a control variables, parameters, attributes. All are same. So this we are having these three parameters. One is del, phase difference, voltage angle difference, and then bus voltage magnitude, and it is only magnitude there, and line reactance. So with this we can understand the concept of facts. I hope you are all following, you're all comfortable, and you're all following, you're able to follow, and you are able to get my point, and you are paying attention towards my lecture. Thank you for your patience. Now let me move on to the next slide. Okay, so I used to tell my students that whatever sometimes they will change the question. That's why I written like this. So sometimes they'll ask necessity of facts, benefits of facts, objective of facts, applications. So the same thing we can try to reproduce according to the question asked. But generally, when I say flexible AC transistor, or why do we go for fax controller? We are aware that whenever we are going to fulfill the load demand, high demand nowadays, we are having a huge demand. So in order to meet the huge demand, we need to plan for expansion or for the power system, or we have to go for the generation of the power. So for that we need to have a so extra power. For that we plan for extra power generation. But you are as we are aware that this is time consuming as well as not economical. That solution is not economical. We try for alternative. The alternative is solution is fax controllers. How it is giving solution without going for example, I need for example, I'm saying I need a 500 watts, 500 kilowatts power. So my requirement is 100 kilowatts. If I'm able to manage with the if I'm able to manage with the existing technique, if I'm able to, then I need not go for installation of new power plant. So this one simple example I'm making you to all to understand the importance of fax controller. And new setup will require the construction of new transmission line. We need to get permission. So and all those things. So complete replacement. When I say that, so what will happen? So more cost is involved. Time, cost, everything is being human efforts. Everything is being involved. So but with available condition, prevailing condition with this fax controllers, we are able to have a control. When I say control, I can increase or decrease both real and reactive power flow in order to maintain the proper real power balance and reactive power balance. So these are the benefits, or we can call objective. Already I told objective. And I have discussed now the necessity and applications. If you see, we have the various power systems studies. One is our problems, voltage stability. I have already told how we are classifying the power system stability. So this transient stability will come under the subclassification of rotor triangle stability. And we can, with the help of flexible AC transmission system controller, one can enhance the voltage stability, enhance the transient stability margin, and power quality issues can be addressed. It can enhance the power quality by eliminating the harmonics. Okay, the TSD value will be less, and mitigate the subsequent resonance, and also power oscillation damping. So oscillations can be reduced. These are the major applications of power fax controllers in terms of voltage instability prevention, transient stability enhancement, power quality enhancement, and then subsequent resonance reduction, and then power oscillation damping. Okay, and let us see the benefits. So both are same only. Once again, I'm repeating this. Kindly bear with me. So load capability of transmission line. So that means to what extent I can transmit the power through the transmission line. So there are some factors which limits the loading capability. So one is thermal limit and dielectric limit, stability limiter. So thermal, due to the ambient temperature or environmental conditions like wind, then conditions of the conductor and ground clearance. This determines this thermal limit. And this our fax cut technology will help us in making an effective use of this newfound line capability. And dielectric, this limits the loading capability, but fax with that we are trying still moving further and reach this loading with in safer side without going for getting into that collapse point. So to what best I can do, sometimes we'll so do your best. That means what? Still something, still we can achieve. So if students is getting 90 marks, we will say that yes, still you try to aim for 100. If even we say that 95 student also, we will say that yes, still you can do better. Still you can do more. So there is something to achieve beyond that. Yes, there is some possibility. So like that only, even though there's some limits of capability, but if we resolve all this issue, one can try to reach its maximum. That is what maximum loadable capability. So that's what we are seeing the solution as fax controller. And we are all aware that so many stability are there. One is transient stability, dynamic stability, steady state stability, frequency, voltage. All these are limiting this power system loading capability. How this fax will address that, we are going to see now. So the important concept we are going to see is how do we classify the fax controllers based on the connection. How do we connect the fax controller in the transmission line? And we can classify into 4 categories. One is series fax controllers, shunt fax controller, series shunt fax controller, series fax controller. Let me repeat once again. Based on the connection, we can classify into 4 categories: series fax controller, shunt fax controller, series shunt fax controller, series. And another classification is there, Can you identify? Are you aware about it? So the second classification is that many of you will be aware about the first classification. The second one they will not take into. They may not be giving much attention on it. So the second way of another way of to classify the fax controller is that variable impedance type fax controller and voltage converter based voltage fax controller. So when I say variable impedance type, how I am able to vary the impedance, or when I say impedance, it is nothing but reactance. So how this transmission line reactance is being varied with the help of this by varying the firing angle of the thyristor. So for that examples are TCSC, thyristor controlled series capacitor, and see here these are all SVC. In there also we have got a susceptance model, and susceptance will be varied. And in voltage source converter based fax controller, these are all emerging fax controller. My topic is emerging fax controller. I'll be discussing in detail about 3 emerging fax controller. Due to time's constraint, I'll not be able to discuss all. So I'll be able to discuss only the operation of the STATCOM, UPFC, to some extent SSC. Okay, so these are my focus. One is STATCOM, and I'll illustrate with the power system analyst toolbox. UPFC second one, I'll be discussing only the operation, and SSC. Other fax control also I will touch. I will try to cover it up in a short manner, in a brief manner. Okay, so the first classification is that based on the connection. So series shunt, series combined operation of the series and shunt, combined series. And examples I have given here. TCSC is the example, good example for series fax controller, and this SSC, static synchronous series compensator, is also an example for series fax controller. And in case of shunt fax controller, we have got a few examples: static war compensator and static synchronous compensator. Sometimes we call it a static compensator. So stat, that first four letters, stat, and compensator, so statcom. And we are adding one more word, synchronous, because it, like a synchronous generator, will this also will deliver a voltage, so it will act as a voltage source. It is modeled as a synchronous voltage source, therefore we call it a static synchronous compensator. And series shunt, we have got UPFC, unified power flow controller. Why it is called unified? Because it is trying to combine the features of the both the fax controller, both the type series and shunt fax controllers. And the interface or interline power flow controller, it has got the feature of combining the both series fax controller. It may be TCSC or SSC. That means by combining two series fax controller, we have this classification. Now when we go for this combined operation of the problem, okay, some will able to perform well as an individual. When teamwork, proper coordination is required. So whenever we are organizing any program, we face issue of coordination. So this coordination comes to picture. So here also, when we are going for multiple fax controller combined operation, so individually it will perform well, but when it is connected together, what will happen? It should be coordinated in a proper manner, and for that coordination techniques are available. That is a research technique. That is one research issue, and if you are interested, you can work on that. You can refer Mohan Mathur book, the last. For that, suitable techniques are available for coordination of and control of fax controllers. What are the issues we are facing? What are the types of interactions? So we face the oscillations. All those, how we are eliminating. That is another one research aspect. If you're interested, you can work on it. Now let me move on to the next slide. So in the upcoming slides, I will be discussing about each and every type of fax controller in a short manner. So I will not give much time. I will not spend much time in explaining it. So series controller, shunt controller, combined series, and combined series shunt fax controller. Now in the series controller, just I'll tell only few points. So see, this is how this is a symbol for series fax controller. It is connected in series in the transmission line, and see the voltage is arrow mark. It is opposite to the current flowing through the transmission line. So that means that will try to compensate with the voltage drop. Okay. Now the series controller can be a variable impedance TCSC. In example for variable impedance TCSC, whereas for variable source Okay, thank you, sir. Sorry for the inconvenience from my side. Due to unstable internet connection, I have lost my uh, due to unstable internet, I have lost my connection. So I will share the screen once again. Sorry for the inconvenience. Now I am using hotspot. I hope this will be. Earlier I was using my college Wi-Fi. Now I will try to share the screen. So one important point to be noted here is, 1 minute. Let me see. My voice is audible. Now the connection is stronger. So okay, in case of serious minute, still my internet connection is showing as unstable. Okay, it will act as a voltage source. Remember that a series fax controller will act as a voltage source, and shunt fax controller will act as a current source. So what do I mean by stating this sentence is that whenever is connected in series with the transmission line, at the point of connection or PCC, point of common coupling. So what will happen? It will try to inject a voltage. So that voltage may be sometimes in phase or quadrature with the line current. Okay, so based on that, it will try to generate or absorb reactive power. We have two components of current. One is active component, high cos phi, and the resultant current will be having two components. One is we can resolve in two components: active component, horizontal component, otherwise real component. Another one component is vertical component, imaginary component, or reactive component. So this point, please, you are. I hope you are familiar with this. And this reactive component is I sin phi, and active components I have given so many names. Active component is nothing but I cos phi. So this will, based on that only, we can say that whether it real power exchange or reactive power exchange is happening. Okay, let me not confuse you a lot. I will tell in a brief manner. This series fax controller will act as a voltage source, whereas shunt fax controller will act as a current source. And already I discussed about the example. One is SSC, and another one is TCSC. So I'll be explaining TCSC in later part. So in static synchronous series compensators, I don't know how many times I need to say sorry to you. Kindly bear with me. It is not in our hand. Okay, let me go fast. So static synchronous series compensator. This is a similar in construction wise. It is same as that of StatCom. I'll be discussing StatCom in detail. Only difference is that it is connected in series with the transmission line. So that is a shunt controller. This is a series controller. Difference between static synchronous series compensator, as the name indicates, it is connected in series with the transmission line, and we are getting a output as a three-phase AC voltage, and it will inject that voltage as a voltage source. It will inject the voltage. See how it is connected. It is connected to this series transformer, and see the primary winding. The current flowing through transmission line is same amount of current flows through the this primary winding of this transformer, to which this triple AC is connected. Okay, that's why we call it as a series compensator. So now the output voltage which will be injected is in quadrature. So when I say quadrature, that angle difference is that 90-degree apart, the output voltage and the line current, transmission current, that is phase angle difference is 90-degree. That's why we call it as quadrature. Okay, and for the purpose of either increase or decreasing the overall reactive voltage drop across the line. Now another example is TCSC. This I'll be explaining in the upcoming slide. Let me tell in a short manner. So this is a schematic diagram for TCSE. We are having a series capacitor. We have got a, this is a inductor and the thyristor valve, back-to-back connected thyristor valve. So together we can call it as a, what is that? TCR, this portion. 1 minute. Sorry, let me clear this. I want to highlight it. Sorry for the inconvenience. Okay, fine. We have got a TCR, that is thyristor controlled reactor. This portion, I want to encircle this. Okay, and we have got a series capacitor. And here the concept is, in case of series compensation, we are trying to reduce this reactive impedance. We need to cancel the portion of the series inductive reactance. So XL will be compensated with the XC. Okay, and the formula for impedance of the transmission is given as Z is equal to R plus J XL minus XC. Or if I'm ignoring the R, it will have only J XL minus XC. So if when I have a control over this XC, by increasing the value of XC, this XL minus XC will be brought down, and because of this IZ, voltage drop, occurring in the transmission line due to this presence of reactance will be reduced, and finally V2, that is receiving in voltage, will be enhanced. Let me repeat once again. Remember this formula. Z is equal to R plus J XL minus XC. So XC, if it is increasing, XL minus XC will come down, will be decreased, and impedance will be decreased. Because of this, IZ will increase, and finally V2, receiving ends and voltage, will be increased. Okay, this is the concept how we are able to have a voltage control with the series compensation, and this we'll be discussing in detail later part. And the sun controller, I told that it will act as a current source. Once again, it may be both variable impedance type, that is example is SVC, or variable source STATCOM. So or it can be combination of both. And now all sun control will inject current into the system at the point of connection. We call PCC, a point of common coupling. So wherever it is connected, it will try to inject. And one important application of this sun fax controller is that there is a nowadays the another research issue is that already researchers have working or worked upon it, optimal location for fax controller, optimal allocation of fax controller. That means when I say optimal location, we need to, excuse me, when I say optimal location, we need to identify the best location so that where the fax controller can be converted, because of which I can enhance the stability. And when I say optimal allocation, how I can the optimal sizing. So what is the rating for which rating I'll be able to get my objective fulfilled. That is the optimal allocation of fax controller. So these are other research issues. First I was telling coordination of fax controller, now optimal location, then optimal sizing, and in STATCOM there are a lot of potential scope available that we'll discuss later. Now in the sudden fax controller, remember it will act as a voltage, sorry, current source. So it will inject a current at the point of connection. I want to inform you that the best location is that midpoint of the transmission line. When I connect the sun fax controller in the midpoint, what will happen? The total line reactance is getting divided equally. So because of this, you remember the formula for real power flow. It is nothing but V1 V2 by X into sine del. So now both the voltage equal. We assume that V1 is equal to V2, that is equal to V. So it become V by X into sine del. Now V square by X into sine del. Now this X is the total transmission line reactance. I told that because of this setup, when I connect the when I connect this shunt fax controller exactly at the midpoint of the transmission line, what will happen is we'll have two segments of transmission line, first part and second part. So from the now two power flow will be there. So in the first segment, what is the power flow? Now the reactance will become from X to X by 2. So what will happen? when I put substitute this x by 2 here, numerator it will be 2v square by x. So what we conclude here is, now in case of compensated system, we are having power flow as the twice, the power has been doubled. Therefore, that is the maximum power 2v square by x. Therefore, we make a conclusion that whenever we do a midpoint compensation, the power is being doubled. I hope you will appreciate this point and you will all agree with my point. Once again, repeating, the best location midpoint of transmission line. Why? Because when I connect there, the line transmission line getting divided equally and reactance x is become x by 2, x by 2. In the first segment, the power flow is nothing but now twice that of the uncompensated system. So that's why we say that it is the best location for connecting the sun fax controller. Okay, now there's a StatCom. I'll be discussing later. First, please let us try to understand the function or definition of this. Okay, this is a example for sun fax controller, and it is an example for voltage source converter based fax controller, and it has the capability of exchanging both real and reactive power independently. That is an important point to be noted. So both real as well as reactive power can be exchanged. When I say exchange, it will observe or generate. And it has two modes of operation. One is capacitive mode, inductive mode. Whenever in capacitive mode, it will generate active power. Whenever in acting in inductive mode, it will absorb reactive power. And already we have seen generation, absorption, reactive power. For that, I told that capacitor and inductor. Capacitor will have, due to its leading power factor, it will absorb generate reactive power. Inductor will, due to its reactive power factor, it will absorb reactive power. Okay, fine. Now SPC, this is another example for sun fax controller, static var compensator. So it can also observe and generate reactive power. We'll be seeing the comparison between the StatCom and static var compensator. When compared to SPC, StatCom is expensive, but future wise it is superior. Which is superior? StatCom is superior to static var compensator. So static synchronous compensator has got superior features when compared to static var compensator. StatCom is better than SPC in performance aspect. So how that will be justified with the help of VA characteristics later part. So now let me try to, now we are discussing only the classification and examples. Okay, and we have got few configurations of SPC. One is TCR, that is thyristor control reactor, and TSR, and thyristor switched reactor, and TCS, thyristor switched, sorry, TSC, it should be TSC. It is typed wrongly. TSC, thyristor switched capacitor. So what is the difference between this TCR and TSR? So difference is nothing but in the case of TCR, we are going to, this concept is very simple. The firing angle of the resistor will be varied, and based on different modes of conduction, what will happen? We can vary the firing angle, and we can make the thyristor to turn on and turn off. And by controlling that, we can control the reactance of the transmission line. Okay, so this is possible in the case of and continuous control is possible with the TCR, whereas in TSR only we will have a discrete control. Continuous control in case of TCR and discrete control in case of TSR. Okay, when I say continuous control, smooth control is possible, and in case of discrete, step-by-step control is possible. And in TSC also the same thing applicable. And I mentioned SVC is considered somewhat lower cost when compared to StatCom. SVC have so many advantages. I think you are aware about it. It will have a fast response. These are all static devices. And third class is the combined series fax controller. What is the example I have given? This is interface or interline power flow controller. We have this is the how it is being connected, and there will be one DC link, maybe a capacitor, in order to which facilitate the real power exchange between the two what is it? Two converters, and it will also accountable for the losses. And we have the last one, combined series shunt. For that example is unified power flow controller that we'll be discussing in detail. And this is how we are having coordination between these two converters. One is series converter, another one is shunt converter. So the best example is unified power flow controller. Okay, so it will have a benefit of combining the both the features of shunt and series controller. And this is what I was discussing, UPFC. We'll be discussing at last. Okay, so the first part I was discussing about few basic concept. and then I started discussing about importance of reactive power. Then I started discussing about the defining the facts controller and classification of facts. Now I'll be taking time to explaining you about few facts controller, its operation or classification. So on its characteristics also. So SVC, static var compensator. So the definition I have shown in this slide. So it is a example for Sun fax controller. It will inject, it will act as a current source. It will inject current, and it has got the capability of generating as well as observing the reactive power independently. Now the output is varied in order to maintain. Okay, ma'am. So in which the output is varied to maintain or control the specific parameters of an electrical power. Okay. Now I have told you the control system parameter. What are those control system parameter? Can anyone text in the chat box? What are those control system parameters? Control attributes, control parameters, or control. I was using three words: variables, attributes, variables, parameters. What are those three control parameters? Based on the equation I have. Do you remember? What are those three parameters? Can anyone text in the chat box? Yes. Okay. One is voltage magnitude, another one is del, and another one is reactance. So those parameters are being coordinated or controlled. Okay, that's why it is written as the output is varied to maintain the control specific parameters of an electrical power system. This is the definition for static work compensator. These are all the advantages or features of static war compensator. I told that it has got many advantages or characteristics. One is less maintenance because of the static part, and fast control, good response, and losses will be low, and high reliability. And then the other advantages is that lack of contribution system short circuit capacity. And this are all, sorry, the last 2 points is not advantage. This will come under limitation. Okay, another harmonics problem. So for that we need to address this issue. Okay, this I'll skip. Once again, the points are repeated here. So static work compensator, it injects the current into the system. That injected current will be in phase quadrature. When I say phase quadrature, is 90-degree apart or phase angle difference with the line voltage. In case of series fax controller, I have told that it inject voltage that will be in phase quarter with the line current. Here it is opposite. Current is injected, because of this injected current will be in 90-degree phase angle with the line transmission line voltage. So because of this, I told that phase quadrature. So we'll be able to exchange. When I say exchange, both generation as well as absorption is possible of reactive power. Okay, in phase means real power, and variable impedance type static work compensator are power electron devices that can control reactive power generation by varying the impedance. That's why it is we call it as variable impedance type static work compensator. SVC types. Okay, these are the configurations or setup or different types. One is TCR, thyristor control reactor, and thyristor switched reactor. Already we have seen thyristor switched capacitor. I have told you the continuous difference between the TCR and TSR. So TCR facilitates the continuous control. TSR helps us to achieve the discrete control. And thyristor switched capacitor, when we need to go for TSC, when we are facing light load condition or peak load condition, when we need to use this TSR, when we need to what condition we should operate this TSR, or it should be operated TSC? Any guess? TSR, when it should be operated, during light load or peak load? What is the future of this TSR? Will it observe reactive power or generate reactive power? Reactor inductor, so it will observe reactive power. So when we are facing the problem of low voltage, when do we face this low voltage? When there is a shortage of reactive power. When do we face this shortage of reactive power? During peak load condition or heavy load condition. I'll repeat once again, please make it thorough. Heavy load condition, we face the problem of shortage of reactive power, because of which low voltage we are facing, and we want to increase the voltage or bring it back to the normal voltage. For that we go for TSC. So to increase the voltage, we go for capacitor, as it able to have a capability of generating reactive power. That is in the case of peak load condition. In case of light load condition, what will happen? Excessive reactive power, because of which we are facing low high voltage or over voltage. This over voltage should be brought down to the normal voltage. For that, the excessive reactive power is being observed with the help of TSR, that is inductive nature. So inductor will observe the reactive power. So TSR will be in light load condition, and TSC will be operated in peak load condition. And another configuration, this is whenever we say this SVC, this is a standard. We'll have to remember fixed capacitor TCR, fixed FC TCR. This is the standard device. Whenever we say the SVC, default it is FC TCR. So we'll have a parallel capacitor, which is a fixed value that will be connected in parallel to TCR. In that case, both capacity effect and inductive effect will be possible. That's why with this setup, we can generate reactive power as well as observe reactive power. Okay. So this is a schematic diagram of FC TCR. So you see here, it is connected in parallel through this coupling transformer, and we have got a back-to-back connected thyristor valve, and inductor is there. And see there, we have got a fixed capacitor that is connected in parallel to this TCR. The left-hand portion is TCR. So that's why we call it as FC TCR. This is a schematic diagram for SVC. And VA characteristics of SVC. So now time is 11:15. I have to go fast. VA characteristics of SVC. There are two characteristics. One is steady state, another dynamic characteristics. So please kindly bear with me. I'll make it little fast. So as you see here, I have given both the steady state as well as dynamic characteristics. Try to observe the difference between the steady state and dynamic. First, let me discuss about the dynamic characteristics of SVC. See the reference voltage. This is the reference voltage. See here, that can be varied. V reference can be varied from between the limits V1 and V2. V1 is upper limit, V2 is the lower limit, or V reference max, V reference minimum. In the text I given as V reference max, and here I have shown as V1, V2. So this V reference can be varied between V2 to and V1. Okay, and we have got a linear range. See here, so this is the linear range. So see the regions. One is linear range, and then slope, and once again we have got this overload range and over current limit. And this is the control range over which SVC terminal voltage in this region or portion, what happened up to this, it reaches this IC, or left side it is capacitive current, right side it is inductive current. Why it is positive, why it is negative? Because what in my understanding, you can correct me if I am wrong, so it draws more current. Whenever we say that it is positive, whenever it delivers back, it is negative. Therefore, I am taking as it is ILR, it will be positive, and ICR. So the IC is nothing but capacitive current, IL is nothing but the inductive current. So now in this linear range of the control, what happened? This terminal voltage will vary linear with the SVC current or reactive power. So and see this slope. This is very important point to be noted here. The presence of slope, it has got several advantages that we will discuss now. What is the slope? It is nothing but the ratio of the voltage magnitude change divided by the current magnitude change. So that is defined as, it is nothing but the gain. So for the amount of current which is being changed, what amount of voltage is being injected or voltage being achieved or changed, that is what, this is the plot between the bus voltage where the SVC is connected and current which is being injected by the SVC. So this is why VA characteristics of SVC, and this slope has got a few advantages that I'll be discussing now. And another region is this overload range. So when the SVC traverses or crosses this linear control range, when we come to the inductive side, this will act as a productive range. So it enter into overload zone where it behaves like a inductor. For that we need to go for this limit, this current. For that we have current, the next portion, that is over current limit. We can say that saturation. So further it should not be current should be increased. For that they see the curve, it is going upward. So we have overload range. So after that, we have got over current limit to prevent the thyristor valve from being subject to excessive thermal stress. So in order to avoid more inductive current being drawn, the maximum inductive current in the overload range is constrained to a constant value by an additional control action. Appropriate action is being taken in order to prevent this entering into that, and we are having a control over this. So this is the characteristics curve for SVC. This is dynamic because it is changing with respect to time. And the difference between the static and dynamic, are you able to observe in the diagram? Only one difference: static characteristics and dynamic characteristics. See, in static characteristics, only this some dead zone is available. See here, for which there is no response. That is the difference between static and dynamic. The steady state VA characteristic of SVC is very similar to the dynamic VA characteristics, except for a dead band in the voltage. So regarding voltage control by the SVC, we will take this case. We will consider a bus where the SVC is connected and the susceptance model is taken into account. And we have got a feedback. We are giving a reference voltage and we are measuring the SVC voltage as input. We are trying to compare with the reference voltage, and based on the susceptance of the SVC is being controlled. And this is it is connected to transmission line which has connected to voltage source. Now let us try to understand the concept of how voltage is being controlled with the help of SVC. The power system now it is modeled as an equivalent voltage source. So here Vs in series with the synchronous reactance behind a equivalent system impedance, that is XS. And okay, the system impedance XS indeed corresponds to short circuit MVA. That is given by the formula that we have studied about per unit calculation, all those things. We know what is per unit actual value, base value. So XS given by this formula. Now let me try to explain with this equation. This SPC will have two modes of operation. One is capacity mode of operation and inductive mode of operation. So as we see in the VA characteristics, in the capacity mode, it will try to deliver the capacity current. Inductive mode, it will try to absorb more inductive current. Okay, so based on the prevailing load conditions. So now see this equation: Vs sending in voltage is equal to VSVC, where the bus in the bus to which SVC is connected, and this is the drop VISVC EXS. See the diagram. So voltage drop is given by the ISVC into XS. So now this ISVC, to make you understand, this is as far as my understanding is concerned, to make it in a simpler manner, I'm explaining this. I told that capacity current will be negative and inductive current will be positive. What is the meaning is that inductive current, it is absorbing more, so plus, and it is delivering back, capacity returning back to it. That's why it is minus. So now what is the formula for VSVC, or receiving in voltage? Vs minus drop, Vs minus ISVC XS. Now ISVC, if it is increasing more, means in case of inductive mode, it will VSVC will come down. Yes, Vs minus ISVC XS. So if I keep on, I increase this ISVC as it is Vs minus ISVC XS. So in inductive mode, the VSVC will come down. And the reverse case, when ISVC is minus, what will happen? Minus or minus, it will be plus. So the VSVC will increase. In capacity mode, voltage is being increased. This is how we have a voltage control with the help of SVC in both inductive and capacitive mode. When I say control, either I can increase or decrease by operating the SVC in both the modes. I hope you are all able to understand and you are able to follow. So now time is 11:25. I'm taking much time. Okay, let me summarize this point. So SVC current result in a voltage drop, that is ISVC excess in phase with the system voltage. This SVC bus voltage decreases with the inductive SVC current. There's important inference or conclusion from this equation. And the SVC bus voltage VSVC will increase with the capacity current. That is how, that what I illustrated, it was evident from my explanation. Okay, and these are the advantages by having slope in the SVC dynamic characteristics. One is it reduces the reactive power rating of the SVC for achieving near the same control objective, and that we are having about the overcurrent limit. It prevents it, and because of that slope, it prevents the SVC from reaching its power limit too frequently. So like a speed break, this slope, it helps us to prevent it from reaching its maximum limit frequently, the transition. So that will being prevented with the help of that slope. That is one advantage. And as it reduces the reactive power rating, so now reactive power will be reserved, and because of which sharing of reactive power among the multiple compensator which are operating parallel, that is also possible. These are the three major advantages for this. 1 minute, give me 2 minutes break. I have to send one mail. I'll send mail and we'll come back. Please stay connected. I have to send one mail. Stay connected. I'll be stop sharing my screen. Please let me take 2 minutes time. Stay connected. I hope you're all able to follow after this. We are busy with a little NAC work. That's why it is urgent. I'm taking time to send that mail to the NAC coordinator. Just 1 minute. Sorry for the inconvenience from my side. Okay, fine. I'm happy to announce you that recently our college we got 4 programs accredited recently. We have received the official confirmation also. We are yet to receive the marks. So under tier 1 we are autonomous. So we under tier 1 we got accreditation, and that is our department also got accredited. So I'm happy to share this information to you all. So 4 programs: CSE, IT, EEE, and EC, and we are waiting for the marks eagerly, and within 1 week we'll get it. So we recently is autonomous also, we have got extended. We have inspections over, and now we are working for NAC. That's why I have sent that mail. Thank you for staying connected. Okay, now let me share the screen once again to you. So around 29 participants are there. I hope you are able to follow. I think now there is no internet connection issue or unstable internet connection. Now it is fine. Okay, is my screen visible? No, I have not shared. Sometimes it is not being shared. Let me try once again. I'm sharing only the PPT alone. I'm not sharing the entire screen. So see that slide is my slide is visible. Okay, fine. I hope you're all with me, and focus. Let your focus be here. So I'll try to complete within half an hour. I thought of completing it by 11:30. Okay, so far we are discussing about SVC, static var compensator. Now let me take time to explain you about TCSC, thyristor control series capacitor. This is the basic model where a series capacitor is there, and to which parallelly we are connecting this TCR. TCR is nothing but setup of series inductor, and we have got a back-to-back connected thyristor T1 and T2. See how it is connected, and we have got a inductor with the inductance of L, and we have let the current flowing through transmission line be integrated as IA line, and IC is the current flowing through this capacitor. Now, with the help of TCSC, one can have a variable series capacitive reactance. So continuous control is possible with the help of TCSC, and see how this is the practical model. Let me skip this because of time constraint. I'm skipping this. These are advantages. I hope you are all thorough with this. I told one advantage is that dynamic control of power flow is possible and continuous control is possible. And there are some applications like subsequent resonation oscillations can be reduced, and DC offset voltage can be reduced, and voltage support. So more or less it will be same, and reduction of the short circuit current. And these are the objectives of variable series compensation, enhanced basic power flow and loadability of series compensate line, and additional losses in the compensate line from the enhanced. These are issues to be taken care. So this also I'm skipping. Now let us come to this point. In the basic model, I told that this TCSC is having two components. One is capacitor and inductor. So I can consider as the parallel combination of LC. So LC, it is nothing but LC filter. So it is LC parallel LC combination. I can consider equal. So I have to let me try to simplify and find out the equal impedance. So you can take time to simplify later, and we'll be getting this equation. And from this, what we concluded is how under which condition it will be able to provide variable capacitor reactance, under what condition it will be able to provide variable inductive reactance. There are two modes. One is capacitive mode and inductive mode. Here also in SBC also I told capacitive mode, inductive mode. That's why we are telling that both exchange. When I say it can generate as well as absorb reactive power. So for that, two modes are required: capacitive mode, inductive mode. Here also, TCSC can able to have a continuous control about line reactance with two modes. One is capacitive reactance and variable inductive reactance. For that, this condition I have given, you can look into it. Now, I already explained this. Let me move on to the next slide. There are two various modes of TCSC. One is bypassed thyristor mode, blocked thyristor mode, and partially conducting thyristor or Vernier mode. When I say bypassed, in bypass road, we'll say that normal route it will go. Some other it being bypassed. So we are skipping that part. So here, see that in the bypass thyristor mode, this inductive effect will be more. How? That will be seen now. Where is the diagram? Yes. See here, as I shown in this diagram, there are three modes. One is bypassed mode, and then blocked thyristor mode, and partially conducting thyristor mode, otherwise called as Vernier mode. So in bypassed thyristor mode, the thyristor we are making to conduct fully with a conduction of 180 degree. That is the condition, and we are applying the gate pulses as soon as this voltage across the thyristor will reach its zero and become positive. That will, what is the impact is, it will result in a continuous unison flow of current through the thyristor wall as shown in this. That is why it is called bypassed. So it will the thyristor is a short circuit, and blocked thyristor it will be open circuit. Here it is the short circuit, so entire current flows through this thyristor wall or inductor. So here it will behave as a parallel capacitor inductor. Both capacitor effect, inductor effect will be there, but see that here it will dominate. Which is dominating? The reactor is chosen to be greater than that of capacitor. So by this setup, in case of blocked thyristor mode, we call it as a waiting mode. Why it is called waiting mode? Because the thyristor is open. So here, by proper firing angle or firing pulses, by proper setup, we can block this. So how we are doing is, the firing pulses to thyristor are blocked. The thyristor is connecting and a blocked command is given. Thyristor will turn off when the current reaches zero. There it is voltage across thyristor reaches zero. Here current reaches zero, and now only it will be a fixed series capacitor, because it is inductor part is open circuit. So only capacitor effect is there. The net TCC reactance capacitive, whereas in the previous case it is inductive. Okay. And third mode is partially conducting mode. It is called Vernier mode. We have two cases. One is capacitive Vernier mode and inductive Vernier mode. So this mode allows the TCS to behave either as a continuously controllable capacitive reactance or a continuously controllable inductive reactance. Okay. So a smooth transition from capacitive inductive mode is not permitted because of this mode. It is like a discrete mode. So these are three modes. This I'll skip. Already I told you capacitive Vernier mode and inductive Vernier mode. See the direction of the current flow. A loop current is there in capacitive Vernier control mode. the thyristors are fired when capacitor voltage and capacitor current having opposite polarity. And see the current of the flow direction of the loop current. That current will have a direction opposite to the capacitor current, and this current increases the voltage across the fixed capacitor. Okay, because of additional current, the voltage across the capacitor will be increased. See the next one. Now it is opposite. Okay, now the current flowing through the inductor, so it is reversed. That we call inductive alternate mode. Here the TCS can be operated by having a high level of thyristor conduction. The circular current direction is reversed, and it presents a net inductive impedance. Okay, so we have completed the classification of fax controller. I have discussed about the SVC. I have discussed about the TCSC, because those will come under the variable impedance type. These are all first, those will come under variable impedance type fax controller, will come under first generation fax controller. Before that, mechanically switched fax controller. After that, first generation, this we have got this variable impedance type, and second generation or the emerging fax controller or the voltage source converter based fax controller, STATCOM, SSC, UPFC, IPFC. STATCOM, SSC, UPFC, IPFC. So I have to complete quickly. I will go fast. Construction work is going on here. That's why you are getting this sound. Sorry for the inconvenience. Okay. So this concept is very important. STATCOM, I'll take time to explain in detail. So STATCOM is nothing but static synchronous compensator. It is sun connected. It is a reactive power compensating device. It has got both the capability of generating as well as absorbing reactive power. It is modeled as a voltage source converter, or it will act as a voltage source. That means though it injects current, that voltage source can be varied, and similar to the operation of a synchronous generator, it will also produce a set of three-phase AC output voltages from a given input DC voltage. Now this DC voltage is provided with the help of a capacitor. Okay, now we'll see in the diagram. The advantage of STATCOM is that it is compact design, small, and it's less low noise and low magnetic impact, and it will have a adjust voltage source behind the reactance. I told that its voltage source can be varied, and it is having a controlled reactive power source. See the diagram. Let us try to take time to understand the construction. When I say utility, this is transmission line. That voltage, let it be E suffix T, utility voltage, and I STATCOM is the current injected or observed I suffix Q or I suffix STATCOM current. Okay, current flowing out of from the STATCOM, and this is a coupling transformer, and this is the another voltage bus where the STATCOM is connected. That is E STATCOM, a converter bus voltage. So to which the STATCOM is connected, and see here, this is a voltage source converter. So that's why we call it as converter based fax controller. Inbuilt is nothing but it is having a voltage source converter, and we have got a DC source, that is with the DC battery we are providing this. And this is the equivalent circuit. This is schematic diagram or power circuit, and in the equivalent circuit we are saying it is modeled as a variable source, voltage source, with a series reactance. And with this we are able to understand when it supplies reactive power, when it absorbs reactive power. We have got very simple. When how do we indicate the direction of the current? So let me not go in detail. I'll stop giving the illustration due to time shortage. So now the concept is very simple. Always there will be a flow of current from the higher potential to lower potential. So now the same thing is happening here. When there will be a reactive current flowing to the utility bus, and when there will be a current flow towards the STATCOM terminal bus. That is very simple, based upon the magnitude of the two voltages. One is utility voltage and the STATCOM voltage. So when the STATCOM voltage is converter voltage is greater than the utility voltage, it supplies the reactive power. When the converter voltage is less than the STATCOM, when ES is less than ET, it will absorb reactive power. That's what I have written here. It is too much text. Let me tell. The concept is very simple. The exchange of reactive power between the converter and the AC system can be controlled by varying the amplitude of the three-phase output voltage (ES) of the converter. Okay, by varying the converter output voltage, it helps us to. The objective of STATCOM is to produce the three-phase AC voltage by with the help of what DC voltage. The concept of inverter is that to convert DC input into AC output. Rectifier is AC to DC. So we'll from the given input, we are getting AC output. And if this amplitude of output voltage increase above that of utility bus voltage, current flows through the reactance from the converter of the to the AC system. And in this case, it will generate capacitive reactive power for the AC system. Next case is that the amplitude of the output voltage, third point, the amplitude of the output voltage, okay, is decreased below the utility bus voltage, then current flows from the AC system to the converter, and the converter absorbs inductive reactive power from the AC system. Now, if the output voltage equals the AC system voltage, the reactive power exchange becomes zero. Both are equal means, in this case, no exchange. Therefore, we call it as a floating state. And this is in the previous slide I discussed about the reactive power exchange. In this slide, I'm discussing about the real power exchange. The converter can supply real power to the AC system from its DC energy source if the converter output voltage is made to lead the AC system. When it lacks, it will absorb real power. Both by this, we are able to conclude that STATCOM has got excellent capability or facilitate both real power exchange as well as reactive power exchange. Reactive power exchange based upon by varying the magnitude of the converter voltage, a STATCOM voltage, and real power exchange is possible by making it to lead or lag with the AC system or utility bus voltage. So this is the VA characteristics of STATCOM. I told that STATCOM has got excellent characteristics or superior to when it is superior to the SVC. See the characteristics curve. In the SVC we have got a linear range. See the linear range here. One important point to be noted or one important advantage is that, as I mentioned here, STATCOM can provide full capacitive reactive output. See here, left hand side IC maximum. It reaches its IC maximum at very low voltage, maybe approximately 0.95, closer to 0.15 per unit. Okay, so even as a very when the load, even at a low voltage, it is able to reach its maximum limit. Whereas in SVC, we have seen that it requires more voltage for reaching its maximum rating. So, but in STATCOM, this is one important advantage to be noted. This is an important comparison. So even as low as 0.15 per unit, it reaches full capacity current. So because of this, another advantage is there. In the case of line outage or outage, the voltage will come down. At that time, it will not affect because minimum voltage is enough for reaching its maximum. So its output of the capacity generation will not get affected because of the outage. Okay. And another advantage is that it can supply both capacity as well as inductive compensation. And it has got increased transient rating in both capacity and inductive operating region. 1 minute. It can be controlled independently of each other. That is already I explained. These are the applications of STATCOM. Dynamic voltage control is possible. Power oscillation can be damped. Transient stability improvement. Voltage flexor control. Real and reactive power control. And we are not going to see application in detail because don't have time to explain all these things. Now the next last one is UPFC. With this I will close. STATCOM I have completed, and UPFC I am going to discuss now. Unified Power Flow Controller. Okay. We have got two converters. One is STATCOM, another one SSC connected through a DC link. Already we have seen about the concept of SSC and STATCOM. STATCOM I have explained in detail. SSC I have just given only a brief explanation. And we have got two transformer. One is a shunt transformer, another series transformer. Through shunt transformer, we are connecting the STATCOM or shunt controller, and through the series transformer, we connect this SSC or the series converter. We are having shunt converter, series converter. The shunt converter may be STATCOM, series converter may be SSC, and sometimes shunt converter can be SVC, and sometimes it can be what is it? TCSC. So, but in voltage source converter base, we are using this STATCOM and SSC for excellent futures. And DC link will help us to facilitate the real power exchange. And this shunt converter is connected through this coupling transformer to the transmission line. And this is connected in series, series converter connected in series with the transmission line. Okay. Okay, I'm getting a message that the same link is being used. So with this, I will try to close. This is a last point. So as I told, we are having two converters. One is shunt converter and another one is series converter. And there are three modes: voltage regulation, series compensation, phase shifting. These are the phase diagram. See that voltage regulation we are having in phase. Okay, here in series compensation, see that VC VC plus V naught will be giving us the VPQ, and this angle can be varied up to 90 degree. So this I'm skipping this part. So this only operation I have explained, and I'm asked to end the session. Yes, I have also completed. I'm not able to demonstrate. Okay, thank you all. Let me end the session now. If you are, I'm happy to interact with you all through this forum. Once again, I thank the management, your college, as well as principal and HOD and coordinator for giving opportunity to deliver this lecture on the emerging fax controller. Thank you all. I wish you all good health at this pandemic situation. Okay, see you all. Now I'm transferring the host option to your Bhuvanesh, sir. Thank you, sir.
Thank you very much, sir. Thank you very much. Information is very, very, very useful.
Thank you, sir.
Thank you very much.
I thank all the participants for their patient listening, for their patience also. And because I was losing my internet connection because of you.
No problem, sir. No problem.
Okay, I'm not able to. I plan to demonstrate, sir, but now due to time, I'm not able to complete that session. And with this, I'll close, sir. Thank you, sir.
Okay, thank you very much, sir. Thank you very much.
You can end the meeting.
Okay, sir. Thank you.